Students, today we are going to study simple harmonic motion. Last class we studied that for any oscillation to become simple harmonic motion, the condition is acceleration must be proportional to minus of displacement. That means what? Acceleration and displacement both should be directly proportional, and the negative shows that both directions are opposite. So this condition, if it is obeyed by any oscillation, then the oscillation is called simple harmonic oscillation. Today we are going to prove that a spring which is attached to one rigid support and to whose other end we are connecting one mass particle m. Then if it is disturbed to one side, pulled one side either towards right or towards left and released, then it makes oscillations which will become simple harmonic oscillations. This we are going to prove today. So now at present we know when the spring is having normal length, then mass particle remains at position O, not to it won't go by itself towards right or it won't go by itself towards left. It is held at position O and the spring has normal length. Then no force acts on it, no restoring force will be produced. Because restoring force, when it will be produced, when the spring undergoes elongation or contraction. Means what? If the length of the spring has become unequal to its original length, then restoring force will be developed. So now at present the spring has normal length, so then the mass particle will not experience any restoring force. Suppose we are pulling to one side like this and released till the point position A, where the displacement is x, direction of displacement is towards right. Then restoring force acts on the mass particle towards left, and that force we know already, F is equal to minus kx. Here minus tells that force and displacements are opposite in direction. See, displacement is what? From particle has displaced from O to A, means what? Displacement direction is towards right, and then restoring force is acting on the mass particle towards left. So force direction is towards left. So in that way force and displacement are opposite in direction. That is why minus. And K is called spring constant. So every spring will have spring constant, that is spring constant K. So this much force will be acting on the mass particle. So this force, if it is released because of this force, it has to go back. When it is coming back, it has to come to O and should be stopped, because at O the normal force won't act. But what happens when it is coming back to O, it will be having some maximum velocity. Due to velocity, it cannot be stopped by itself. That is the law of inertia. So it goes to further towards left of the position O. So till point B. Again restoring force will act, and by which it should go back towards right. So it will be going back again. When it is going to O point, again velocity become maximum. So it cannot be stopped because of law of inertia. So it further moves towards right till point A, where velocity becomes 0. So in that way it will be making oscillations through point O between extreme points A and B. It will be making oscillations. These oscillations we are going to prove, those are SHM. So at first to prove that one, what I am doing, when a particle is at point A, I am observing. Then it is experiencing force how much? F is equal to minus kx. But that force we can equate to minus kx, we can equate to mass into acceleration, because that is the net force acting. So net force is always equal to mass into acceleration. From this, acceleration is minus k by m into x. And k is one constant for given spring, and m is also, it is the mass of a given mass particle, which is a constant. So if you remove the constants, we can write this: a is proportional to minus x. So this indicates that acceleration is proportional to displacement, and minus tells that both are opposite in direction. So which is the condition of SHM. So in that way we reached the condition of SHM. Means what? This particle will oscillate between extreme points B and A through point O. These oscillations have definitely becomes simple harmonic oscillations, we proved. Now last class we got in case of SHM, acceleration expression is minus omega square x. With this equation, these two equations I am comparing, then omega square value is become equal to k by m, and omega is called will become equal to root k by m, where omega is called angular frequency. So its expression is 2 pi into normal frequency n, that is root k by m. So from this, n is equal to 1 by 2 pi root k divided by m. In that way we got the expression for normal frequency, linear frequency. If then time period expression means what? Reciprocal of frequency 1 by n, that is 1 by 2 pi root m by k. So in that way, we found that expressions for time period, frequency and angular frequency. So with which the particle is making simple harmonic oscillation. Dear students, today we are going to prove that a pendulum also can make SHM. So let us consider a simple pendulum. This is rigid support to which thread. This is a pendulum. Pendulum is what? Small mass, point mass, one spherical body, small spherical body whose mass is at the center of mass, center. And this is called length of the pendulum. We show with the L. Now this is at point O. Now if you pull this to one side, either towards right or towards left, and release it, it will make oscillations like this. So these oscillations will become SHM. That we have to prove. So that means what? In that way it oscillates. So these are A and B are called extreme points and O is called mean position. Now this is the C point around which this is oscillating, making angular oscillations. These are not linear oscillations. In case of spring, what is that? This is a rigid support and spring, and to which one mass particle is attached, and if it is pulled to one side, then it was oscillating between these two extreme points like this through this midpoint. Midpoint के द्वारा ये extreme points के बीच में ऐसा linear oscillations कर रहा था. Those are called linear oscillations, linear simple harmonic oscillations. But here pendulum is pulled to one side like this and released. Then it makes angular oscillations around center point O. This is the center point. Center point around angular oscillation, rotational oscillations it is making. So these are also called becomes SHM. That we have to prove. To prove that one, when it goes to B point, I am observing. When it goes to B point, you know how many forces will act? Two forces will act. One is mg, force of gravity, which acts vertically, and other force is tension force, which acts by the rigid support towards rigid support. So that is called T. In that way, two forces are acting. Then what we will do here? If this is this angle is theta, then if you just produce this like this, this also become theta. Then this mg we can split it into two components along this direction, which is making theta angle. Mg is in vertical, its component will be mg cos theta, and other component will be perpendicular to this component, that is like this. That is mg sin theta. See, in that way, mg we have split it into two components, mg cos theta and mg sin theta. So out of these two components, mg cos theta is balanced with t. That is why you can get one equation, t is equal to mg cos theta. Now without undergoing variance, which force is left? Mg sin theta. So due to this force, it has to come back. When it is coming back, it is rotating about C point. Means what? Because of this force, rotation is developed. Rotating effect is produced. So rotating effect is called torque. So a force के कारण torque is produced. So torque, how to find out? Torque is given by, tau is given by force into perpendicular distance. Force how much? Mg sin theta. And perpendicular distance from where? From point of rotation. Point about which the particle is rotating. This particle is rotating about this point. This point we are treating as center. So from center to distance to the force direction of perpendicular distance. So which one? The length of the pendulum itself become perpendicular distance from point of rotation to the direction of force. Mg sin theta is a force, which is acting like this. To that force, the perpendicular distance is L itself. So that is why torque is given by force into perpendicular distance, that is L. So these are torque. And this torque, torque we have to equate to what? General formula for torque is I alpha. We studied, where I is called moment of inertia and alpha is called angular acceleration. I is called moment of inertia of the pendulum, which is rotating, and alpha is called angular acceleration. So theta we can ignore, sine we can ignore here for small angles. Then we can write mg theta L is equal to I alpha. And also I want to put here minus. Why minus? Because due to torque, when it is coming back like this, the angle is decreasing, theta. torque is increasing. So because of torque, angle is decreasing to show that point to minus. So one side if you put minus, then from this alpha will be equal to how much? Minus mg L theta divided by I. Here I means what? Moment of inertia. Moment of inertia of this pendulum. How we will get moment of inertia is, see, this is a point mass. Point mass which is rotating about center. Then moment of inertia is mass into radius square. Mass is m, radius is L radius. So m into L square. That is the moment of inertia we can replace with the, we can replace with the m into L square. So minus mg L theta by m into L square. M got cancelled, one L is got cancelled, minus g by L into theta. Now, so here angular acceleration alpha, we got minus g by L theta, in which g constant for a given place, acceleration due to gravity, it will change from place to place, but at one place it won't change. Length of the pendulum is a constant, so g by L is constant. That means what? Angular acceleration is proportional to minus theta. So this is acceleration and this is a displacement. Both are directly proportional. So acceleration and displacement both are should be directly proportional, and minus indicates both are opposite in direction. This is the condition of SHM. That means we have proved that simple pendulum makes SHM. But only in which condition in which context it is making SHM? When we ignored here sine. Sine will be ignored when sine theta we have replaced with theta. So means what? Sine part ignored. It happens when angle is very small. Means what? When angle is very small, then only the oscillations will become SHM. If you pull the pendulum to large angle and release it, then it oscillates, those oscillations will not become SHM. That is why you should remember that point. Okay, after proving that the oscillations have become SHM, then I am comparing this equation. Which equation? Acceleration is equal to minus g by L theta with we know acceleration is equal to minus omega square x. So x is here a displacement and theta is here displacement, and a is acceleration and here alpha is angular acceleration. So if you compare these two equations, omega square must be equal to g by L. That is why omega square is equal to g by L. Then omega is equal to root g by L. So in that way we got the expression for angular frequency with which pendulum oscillates. So after getting angular frequency, omega is equal to root g by L, then omega means what? 2 pi by t. So 2 pi by t is equal to root g by L. So from this t is equal to 2 pi root L by g. In that way we got expression for time period, and normal linear frequency is 1 by time period, that is 1 by 2 pi root g by L. In that way we got the expression for time period and frequency and angular frequency with which pendulum makes SHM. So dear students, we are going to verify whether ideal SHM obeys conservation of energy or not. Means what? Total energy, whether it is conserved or not in case of SHM. For that I am reminding you the expression for displacement x is equal to a cos omega t, where a is called amplitude and omega is called angular frequency. And velocity expression also we know, that is v equal to minus a omega sin omega t. In that a into omega becomes the maximum velocity, v not maximum velocity, a into omega, and omega is angular frequency. So we know expression for position or displacement at any time t, and velocity expression at any time t we know. So when you know these things, you can write first kinetic energy. Kinetic energy is given by half m into velocity square. That means what? Half m velocity we know, so minus a omega sin omega t whole square, because see velocity is minus a omega sin omega t. So half m velocity square means what? Half m into velocity square. So if you square that one, it will become half m a square omega square sin square omega t. This is the expression for kinetic energy of SHM करने वाला पार्टिकल का किसी भी समय में kinetic energy का एक्सप्रेशन आ गया. अभी पोटेंशियल एनर्जी का एक्सप्रेशन. पोटेंशियल एनर्जी स्प्रिंग के विषय में पता है हम लोग फार्मूला. पोटेंशियल एनर्जी फार्मूला क्या? स्प्रिंग के विषय में हाफ के एक्स स्क्वायर, लेकिन स्प्रिंग के विषय में ओमेगा स्क्वायर इज के बाई एम, ये भी पता है. सो इसी से के क्या होता? ओमेगा स्क्वायर एम. दैट इज बाई के को रिप्लेस करें तो हाफ एम ओमेगा स्क्वायर. into x square. X means what? Displacement, that is a cos omega t. So x square means what? A square cos square omega t. That equal to that is how we got the expression for potential energy also. So we have expression for kinetic energy and we have expression for potential energy. If you now you want to find out total energy, whether it is constant or not, we are going to check now. That is why total energy means what? Sum of kinetic energy plus potential energy. That means half m a square omega square into sine square omega t plus half m omega square a square cos square omega t. So in both what is common? Half m a square omega square is common. Then here sin square omega t and here is cos square omega t. That is equal to half m a square omega square into 1. That is half m a square omega square. Now check the answer of total energy, half m a square omega square. Half m a square omega square, in which neither time is there nor position is there. That is what? Total energy is constant. Here itself verification is done. Now I want to do this verification once again, not by using time. Here position was depending on time, velocity is depending on time. Without taking like this time dependent position, time dependent velocity, we will take in another way. Once again I am going to verify how. See, we know position is given by x and velocity is given by v. Velocity, one more formula we know, minus omega root of a square minus x square. So there what we wrote, velocity is equal to, as a function of time we wrote. Now velocity as a function of x, position. So by using these two we can find out kinetic energy and potential energy. Kinetic energy is given by half m velocity square. Half m velocity means this much. So minus omega root a square minus x square whole square. If you expand this one, half m omega square into a square minus x square. This is the expression for kinetic energy. Now potential energy is given by potential energy. In case of spring, you can use half k x square. So half k means what? M omega square in case of spring, x square. So this is the expression for potential energy and this is the expression for kinetic energy. The difference is earlier when we did energies, both were depending on time. Now both kinetic energy and potential both are depending on as a function of x, position. Now let us find total energy. Total energy, if we find kinetic energy plus potential energy, that is equal to half m omega square a square minus x square plus half m omega square into x square minus x square. This is kinetic energy, and potential energy is half m. This is potential energy. Potential energy, half m omega square, half m omega square x square, half m omega square x square. So if you expand this bracket, one term will get cancelled. Again you will get back half m omega square a square. So that means what? Total energy, again same answer we got, total energy now also. Now this is neither depending on time nor depending on x. That means total energy is constant. So conservation of energy, so I have proved. Dear students, listen here. Now how kinetic energy, potential energy and total energy, all these three, how they are varying with respect to time and how they are varying with respect to position, graphically we have shown here. See, position x is equal to a cos omega t in case of SHM. Then potential energy is half m omega square a square cos square omega t. Similarly, velocity is minus a omega square omega t. Then kinetic energy is half m velocity square, that is minus this one. So this expression of kinetic energy, potential energy depends on time and kinetic energy also depends on time. So both we show graphically. Here this is the time axis t, small t, and time axis per oscillation time period hatana. So a 0 time, a 1/4 of the time period, a half of the time period, a 3/4 of the time period. This is full time period. And first potential energy graph, it consists of cosine function. Cosine function won't pass through horizon. It will come from maximum to 0, 0 to maximum to 0, 0 to maximum. This is cos square function. It won't go down because square function is what? Positive function only. Negative won't go there. Similarly, kinetic energy formula में क्या है? Half m omega square a square sin square omega t. Sin function will go through horizon to maximum to 0, 0 to maximum to 0. So this is how kinetic energy is changing. So on earlier first graph is kinetic energy. First graph is potential energy. First graph is of potential energy. So here I wrote wrong. This first graph, this graph is of potential energy, not kinetic energy, and this graph is of kinetic energy. Kinetic energy. Kinetic energy. So in that way, both energies are changing. But total energy is a constant. See total energy. Total energy expression half m omega square it should be constant. So that graph is this. This is a total energy graph. Straight line is a total energy graph. So all the three energies I have shown how they are varying with respect to time. And this time, those three energy variations with respect to position. See, this axis is energy on which total energy, kinetic energy, potential energy, all the three energies will be shown. And this axis is position, x is 0 position, x minus x position, plus x position. Now, when the particle is oscillating like this, what is the expression for kinetic energy, potential energy half m omega square x square. So means what? It will be maximum at extreme points. So here maximum and become 0 at mean position and again become maximum. This is the variation of potential energy. And kinetic energy, if we check that kinetic energy is half m omega square into s minus s square. It will be maximum at the mean position. At extreme points it is 0. So 0 to maximum, maximum to 0. This is regarding kinetic energy. And total energy will remain constant, that is regarding total energy. So here also there are three graphs. This is kinetic energy, and this one is the potential energy, and this is the total energy. In that, total energy is remaining constant. So that means what? Total energy of the ideal oscillation, ideal SHM will remain always constant. But if there are not ideal oscillations, if the oscillations are not ideal oscillations, real oscillations where amplitude gradually decreases and becomes 0, then oscillation will die. In that case, there are friction forces will be there. So due to friction forces, then total energy gradually converts into heat energy and energy will be lost. Finally, oscillations will die out. But in case of ideal oscillation, total energy will remain constant.